Um, Okay, that's not the last lecture that I'll give. So this time we will talk about the most difficult part of my part of the course, the similarity theory. And we will talk some more about the surface layer. Okay, just some revision. So we have been talking about two different types of turbulence production. One is buoyancy, right? But buoyancy could be production or loss. And then another one is the mechanical turbulence production. And if we show you this kind of graph, like you have a shear here and turbulence is easily produced, that is talking about the mechanical, right? It's always about the dynamical part of the whole system, right? So you have shear and then you have turbulence. So here you don't need to have shear, right? It's all coming from the surface. The thermal is coming from the surface. Okay, so two very different mechanisms here. Okay, so we know that in the mixed layer, it would be buoyancy dominated, of course, during the daytime, right? This is a daytime profile. And at the surface layer, you might get much more shear domination. So shear could be dominating this part of the planetary boundary layer. But it's not always the case. So this time we will get into details of how do we assess the situation. So this layer, if it is dominated by shear or not, or just buoyancy also, okay, we'll get to that. Okay, and then we will also talk about normalization. Okay, how do we align all the things on the same scale? Okay, on the left-hand side, we have measurements for the different flux, heat flux, moisture flux for different heights. But you have a plane, right? You have a plane flying, and your PBL height could be changing over different times of your measurements. So what you need to do is that you don't need to care about the times. You just do the normalization, right? Or dimensional analysis. This is called dimensional analysis. We make everything dimensionless. Okay, the height here is you have no unit here anymore. So it's a relative height relative to your boundary layer height. Okay, so if you do that, your measurements could be looking more systematic. Okay, they will give you a pattern, just like this heat flux. We have studied this profile many times, right? So you have nothing on the left-hand side. So this time we will use this concept to understand what similarity theory is. Okay, and another type of normalization. So here, this is an example. So I've shown you this, right, in lecture 7. We talk about normalization of all the TKE terms with the magnitude, with the surface magnitude of the buoyancy term only. Okay, so this is 1 because you have divided the whole equation with just the buoyancy, the value of the buoyancy term here. Okay, so Okay, so this is, I want to show you why, I want to show you, we have already talked about this, the normalization of different terms. Okay, we also have talked about the different properties of the surface layer. Okay, the arrows here are not accurate, actually. It's the log mean profile starts here. Okay, so we have constant K from the K theory, and then we have changing K all the way. So the surface layer, for the surface layer, we have the mixed length theory, right? Mixed length theory is telling you that we have different K. We have K as a function of the height, okay, or the eddy size. Okay, so this is like a summary for what we have learned last time. We have learned about the K theory, right? The K theory is relating the large scale stuff, the theory, right here, the shear, and the small scale stuff, the flux, the momentum flux. So it's relating the two of them, and it's a down gradient theory. So things is moving from the high gradient to the low gradient. So that's why I have a negative here, right? And then you have the mixing length theory. It only applies in the surface layer, right? So the mixing length theory, we have done the mathematical interpretation for that. So we express K. K is no longer a constant in the surface layer. We express K as, again, as a function of the shear. Here, this is also an assumption, mixing length theory in the surface layer, because we assume that the lower the layer, the shorter or the smaller the eddies are. So we apply this to this L here. It doesn't mean anything here, actually. This is just talking about the length scale, okay? And then we also have another assumption for the surface layer, constant flux. So this is constant, and we have another variable to represent this constant flux at the surface layer, okay, U asterisk, or you just call this U star, okay? So we also have talked about the log mean profile last time. The log mean profile is coming from the K theory and the mixing length theory, which are all approximations. Okay, this is first order approximation, remember that. We use this because it really matches with the observation, with the natural stability situation, okay? And we assume that we have constant flux at the surface because this is a sample profile, okay? But you can see that at the bottommost part of this profile, we have a rather constant. It's changing, but it's changing very slowly. So we assume that this is constant, and we can use this assumption to calculate something else, right? Okay, so that's why we have a log mean profile. Okay, so last time you have done 8.2 classwork. We have given you this profile, which is like a reverse log mean profile, right? This is wind, right? And we just want to include the two X and Y dimensions. So M is the horizontal wind speed, okay? You have a log mean profile. So this one is like the reverse version of this one. So we have a log mean profile, but we put a negative sign here. So it's the other way around. And we asked you to express the flux in terms of height, and it turns out that it doesn't depend on height, right? So why do we have like a changing profile for the potential temperature, but the heat flux, sorry, this is heat flux is not depending on the height, right? This is depending on the height. We have a height here. So after you have done the in the differentiation, you found that, of course, C is gone. Okay, it doesn't depend on height, it's a constant. It's a constant. It's kind of a constant, right? If A is a constant. For common constant and U asterisk is constant for the surface layer. That's because, okay, you have different slopes here, right? You have different slopes here. You might assume that you have different, your heat flux might perform differently. But in the lower level, because you have another assumption, you have the mixed length theory assumption, right? In the lower part of your surface layer, the eddies are smaller, so they're less effective, which compensates the change of this slope. Okay, you have larger eddies here. Okay, even though the slope here is not steep, right? Then you have the compensation also. Okay, so you have done the differentiation and found that mathematically, but physically, this is due to the, your another assumption, different sizes of eddies. Okay, so that's why you have, this is heat flux. Sorry, I have a typo here. Sorry about that. So that's why it doesn't depend on height. Okay, if you have more questions, you can talk to Leo. Okay, so this is the main theme of this lecture, so the Obukhov length. So before we talk about Obukhov length, we need to go back to the TKE budget equation. So these are the different terms, the change of the TKE, and then the buoyant production and loss, and then the mechanical shear production, right? And then we always ignore this one, pressure correlation term, because they're too small, okay? And this one is just moving your TKE around. So we have one question about this in the midterm, right? So it's just moving around. So it's not generating, or it's not TKE dissipation, right? So this one is the dissipation, which means that you always generate turbulence by term 3 and 4. And then the turbulence always dissipated here. Okay, production and loss. Maybe this one sometimes is lost. Okay, buoyant loss sometimes if you have a very stable condition. Okay, so but the mechanical part is always positive. It's always production. Okay, so we want to normalize the whole equation by the surface properties, right? We have a subscript S here. It means that it's for the surface layer. And we replace, or we divide the whole equation by the surface properties here, the surface flux. This is constant, right? It doesn't matter if you do the division. Okay, we multiply the whole term by this. Somehow it's related to this friction velocity. Okay, we multiply the whole equation by this. Why do we make it like this? Why do we multiply the whole equation with this? Because we want to make the whole equation dimensionless. Okay. If you think about it, for example, the term 4, you have 3 momentum terms here, right? You have the power to the U asterisk, the power 3, right? You want to make it dimensionless, so you need to have the right amount of the variables with the same units, right? And then Z here is crossed out by this C. So if you multiply the whole equation by this term, you will make the whole equation dimensionless. There will be no dimension. And K doesn't have a dimension. It's a dimensionless number. It's called von Karman constant. And it's experimentally found, okay, the value. So why do we put K here if it's a constant? It's an important variable. It might change over different situations. So we need to put that in. So now the TKE budget equation becomes this one, very complicated. It looks like it's very complicated. 3, 4, and then the last one, which is the dissipation, the 3 terms. So in this lesson, we focus on these three terms. Okay, so repeating things again here. So the whole TKE equation, and we multiply the whole equation by this to make it dimensionless, and then it becomes these 3. So now we have a new parameter here, which is called Obukhov stability parameter. So how do we look at this? So we have Z here, which is the height, right? And then everything else belongs to this big L. So you have the expression of this big L. So everything here is constant because it's for the surface layer. So there's a chance that you can do measurements and then you can find some of the variables that you don't have because it's constant, right? So here things are dimensionless. This one is dimensionless, right? Height over height. So it's dimensionless. But this L has some meaning in here. Okay, so you have divided, or you have multiplied the whole term by this one, right? So U asterisk somehow is related to the mechanical part, right? The mechanical part, or the momentum flux of your turbulence. So if you look at term 3 is for buoyant, right? Buoyancy. So if you look at term 3, you have 2 mechanisms combined here. So the first one, of course, is because it's coming from term 3, right? You have the buoyant production or loss. And because you have do the multiplication, you will see the shear production here too. So somehow this Obukhov stability parameter is telling you the relative strength of these 2 mechanisms. Okay, so it can be used, this parameter can be used to identify the relative contributions of these 2 mechanisms, the buoyant production and the shear production. And sometimes the buoyant is not production, the buoyant is buoyant loss. It's the buoyant loss we're talking about. So we need different signs. So if this, is it called theta, this Greek theta, right? So if this Obukhov stability parameter is less than 0, then you have unstable situation, and then you have positive buoyant production. So it all traces back to the TKE budget equation. So you have positive or negative buoyant production or loss, right? So if it's larger than 0, then it's a stable situation, and then you have negative buoyant production, which is buoyant loss. Okay. So L here is the physical meaning of L here. You can rewrite the green part in here as L. Okay, the red part is representing the shear production, and the blue part is representing the buoyant production and loss. And L has a physical meaning. So it's telling you where the buoyant factor first dominates over mechanical shear production. So you have, assuming that you are looking at the daytime profile, right? So the daytime profile, you have a lot of thermals here. You might have some mechanical generated turbulence here. So how far do they extend, right? How far do your mechanical shear production extend? Or what is the extent of your buoyant production or loss? Okay, so we need to have like a relative comparison between them over height. So it has to be a function of height. In my part of this course, we always talk about the vertical dimension, right? We always ignore the horizontal change. So it should be a function of height. So this graph is a little bit difficult to understand. So I just shift the direction from the textbook Okay, the textbook is like 90 degrees to the left. Okay, so here the vertical dimension here is the height or the dimensionless height. Okay, Z over L. So this is a profile coming from measurement. So we have different contributions here. Of course, the two most important ones are from term 3 and term 4. Term 3 is the buoyant production. Okay, so it's coming from measurement. So you can see that it's getting larger and larger, more and more important in the upper part of the PBL. Okay, and shear production, it's rather flat. It has some, okay, on the right hand side here, it's positive. It's TKE gain, right? We have TKE loss in here. So we only focus on these two. So you can see that shear is larger near the bottom because you have larger shear, right? The shear production is larger. So if you change the value of L in theory, right? If you change the value of L, you can have different situations. For example, if you have like a higher L here or a smaller L here, so this profile would be compressed, right? If you have a smaller profile in here, so your buoyant production probably dominate the whole, almost the whole PBL, right? And here you might have some part which is shear dominated, right? If you have like a larger L, right? So this L means something. It means how much you stretch this profile. Okay. You might still get some shear generators in here, but we from the big picture, we know that almost all layers are dominated by buoyancy, right? So this is the meaning of L. So you, of course, you can separate different parts of this profile. If you are at the middle of L, C equals to 0.5 L, half of the value of L, then you know that their importance are very much similar to each other, okay, approximately equal. And if you are at a higher level, the buoyancy is taking control over the shear generated profile here. And of course, if it's much smaller than L, then you know that it's shear dominated, right? So it's like separating different regimes here. Okay, I have already explained this. And this one is for the neutral conditions where you don't have a stable or unstable situation. It's just simply neutral. So they are never touching each other. Okay, so this is probably from the measurements. So we have positive L here in the y-axis and then negative L here. Okay, and you know that if, okay, this is showing you the change of L over different time, over a day. Okay, so the change, if it's looking like this one, or if it's looking like this one. Okay, that's the meaning of this graph. So if you have small L, which means that you have this kind of situation, right? Small L. If you have small L, you know that it's buoyancy dominated. So you can see that after sunrise, the value of L decreases, right? Decreases over time. And then you have like a large uncertainty range here because you have different situation over different days, right? But you know that if it's closer to the small values in here, it's buoyancy dominated. So at nighttime, it's also going to like a smaller value in here, smaller magnitudes in here, because at nighttime, it's also the buoyancy also is dominating the situation because you have a very, very stable situation at nighttime, right? So that's why you have smaller magnitude of L. okay? So this is a graph showing you the relationship between the U asterisk, the red one here, and then the Obukhov length. So we are showing you the relationship between this red variable and L here. So how does it change if you change different terms in here? For example, the heat flux, this one, if you change the heat flux, what would happen? Okay, or if you change the Obukhov length, what would happen? So of course, if you have larger shear or friction, your Obukhov length increase. Okay, due to, you can look at the math here. So this one increase, and then this one also increase because your layer, the friction influence layer becomes thicker. So this one is constant, right? But it can be larger over different situation. Okay. And you can, for example, if you look at this flash, this line, this dashed line here. So you have the same shear influence, right? On this line, you have the same shear influence because you have the same U asterisk in here, right? So if you increase your Obukhov length going up, increase your Obukhov length here. What does it mean? It means that your shear is decreasing, right? You have different values of shear here. The shear value is decreasing, so shear value is decreasing. So the higher the heat flux, you will reduce. The higher the heat flux, you will reduce L. Why? So if you go down, your heat flux is larger, right? You will reduce the value of L. Okay, if you have increased your value of heat flux, you will reduce the value of L, just like this case. Okay, we have talked about the molecular transport, right? We have been talking about the turbulent transport for a while now. So this time we will get to the part where we talk about the molecular transport. So what is molecular transport? You have random motions in here, right? You have the random motions, which are the red arrows in here, but you have like the organized motion, the green one. So you know that even if you have shear, you have random motions in your molecules, right? So the random motions in your molecules will transport your properties. For example, from the higher wind speed layer to the lower wind speed layer through this vertical motions from the random, from the random motions. Okay. So if you blow, so this is the heat flux. If you blow this part up, like the smallest one or the very thin layer closest to the surface, you will see that the total effective turbulent flux, of course, it looks constant, but it's really coming from two terms, the turbulent flux term and then the molecular flux terms, if it's within 1 centimeter from the surface. So in this course, we always talk about this, the effective turbulent flux, which is the sum of these two. Okay, remember that. Okay, so within a thin layer, again, we use the down gradient approach. So the change of temperature will drive the heat flux. Okay, and it's down gradient from high to low. And then this one is, you can think of it as viscosity, but here is called molecular thermal diffusivity. And okay, this is just a reference value. It's very, very large. Okay, that's why when you go to a beach, you can feel that it's really hot under your feet, but it's not that hot in your body, right? So this is what it means. You already have felt that. So, in summary, we can ignore the molecular processes in equations like this because we have included them in our assumptions. Okay, I think I will skip this one. Okay, maybe I'll talk more. Okay, so here, if we apply this constant flux layer to the surface, the constant surface flux, this one, if we apply this to the surface, there's a subscript here. So the next step, so we have done this for the surface layer, but we have to parameterize it in the surface layer and also in the air-land interface. So the two things we have already talked about this, right? In the surface layer, how do we I think we haven't done this. So how do we express this for different terms, especially height? Okay, for the two situations, just the surface layer and the surface, the interface between the land and the air. Okay, so maybe we can take a break. 10 minutes now. Okay, thank you. Okay. So two of you asked what is the difference between having this L and the Richardson number. Okay, so here you are doing the multiplication to make the whole equation dimensionless, right? Why do we need to make it dimensionless? We want to have we want to have the comparison according to the height. Okay, so that's one of the reasons, right? It's not just simple comparison. We want to have the vertical profile of the relative importance here. So L here is very important. C here is very important. Okay, we'll have further elaboration on the Obukhov length stability term. So we need another family of parameterization in the surface layer. Okay, so now we have the normalized TKE budgets here, right? So similar to term 3, we have already dealt with this term, right? We have dealt with term 3. C here, and then we extract everything else as the big L, right? And here, if we focus on this shear production term, this one is the momentum flux. So by definition, it's basically the same as this one. So we ignore them, and then we take everything else here, the orange ones here, and then we define that as the dimensionless wind shear. So we have a wind shear term here, but we have to do the multiplication, right? We make it dimensionless. So why do we have this dimensionless wind shear? Okay, so if we measure something in the environment, for example, if we do local wind measurement here, the blue term here, and if we know this phi, somehow if we know this phi, if we know the profile of this phi, we can estimate the turbulent flux. Okay, so in this part of the lecture, we want to parameterize this over height. So if we have a profile for this, if we like have a universal profile and it applies in different situations, we can make use of this equation and guess the constants in here. Okay, so that's the whole idea behind this. So so repeating the things, we have the dimensionless shear, and then we have the Obukhov stability parameter. This is coming from term 3. This is coming from term 4. Okay, so what we want to do, the aim here is that because this is like the normalized height, right? The Obukhov length is the normalized height. This is the normalized shear. Both of them are normalized. Both of them are dimensionless. So what we want to do is that we want to express this dimensionless shear in terms of this Obukhov stability parameter over this dimensionless height. Okay, so if we have this universal profile, then we can apply this to different models, different situation, different measurement situations that you have. So it's very similar idea of expressing your shear in terms of height. Okay, but you have dimension. So the Moline-Obukhov similarity theory, I think they are both Russians. Okay, it's also called surface layer similarity, or you just call it similarity theory. So now we have the dimensionless wind shear, and we assume that it depends on, we don't know yet here at this stage of the lecture. So we assume that it depends on the dimensionless height. Okay. So we arrange the equation, just the same equation, rearrange, and then we assume that this one is depending on the dimensionless height. So which means that your wind or your wind profile, the change of your wind according to height, is also depending on the surface properties, the U asterisk and L here. So L is controlling the relative importance, right? So it's telling you different things. Of course, it's telling you the change of your wind profile for height, and also the momentum exchange at the surface. And also here, this one, which is coming from the buoyancy effect, right? Different effects here. This one might be somehow related to shear, right? This one somehow related to your buoyancy production or loss. Okay, so you include different factors in here, different physical meaning in here, right? The two of them. So, which means that your shear can be a function of these three, right? Okay, so again, this is very similar idea of expressing your shear with height, but now we include extra two terms which are coming from the two effects. Okay, so that's a physical meaning here. So this is how we do the parametrization. Okay, this part where everything is very messy in here because it's empirical. Why is it empirical? Because it's coming from measurement. Okay, so the x-axis here is the dimensionless height. We have positive and negative because we have stable and unstable situation. Okay, and then we have shear. We have the dimensionless shear on the y-axis. So, which means that this graph is telling you the strength of your shear over different heights, but they are all dimensionless. Okay, and the two signs here representing stable situation on the right-hand side, the positive side, and unstable situation on the left-hand side. Okay, so we have a range of uncertainty, but miraculously, all the dots you can find from the experiments, they lie along this line. It must have some meaning, right? It's not coming purely from theory. It's not coming from like Newton's second law. It's not something like that, but it's something that we found in observations. So boundary layer meteorology cannot live without the observations. Okay, so we have different profiles, which is coming from the curve fitting, right? So how do we interpret this? It has some meaning, right? If you have unstable situation, then your shear is larger if you are at a smaller at a place where it's closer to the surface, right? This is larger magnitude. It means, right, you have like almost close to 1, right, at the surface, and then you have very small values after that or above. So shear dominated layer, and then this is not shear dominated anymore, right? So this is telling you the same thing as this one, right? So shear dominated closer to the ground and not shear generated above, right? So this is the meaning of this. And here you have stable situation. So the shear It's stable, right? It's, you have negative buoyant production or consumption, just buoyant consumption. So it's all due to, so the turbulence is generated purely from the mechanical process on the right-hand side, so stable. So if you have a larger height, then your shear is also larger. Right? This is telling you this. So these two are only applicable for the unstable condition, which is for the left-hand side in here. Okay. For the stable condition, buoyant loss dominates on the right-hand side, even if you have shear. Okay, so because we have defined the dimensionless wind shear in here, we have wind shear and the normalized term. Dimensionless wind shear, depending on the height, we have the parametrization for that. So so-called parametrization is this, okay? We parameterize it over some of the terms that we know. This is called parametrization. Okay, so which means that if we have this relationship, this empirical relationship, if we have the height or the Oberkopf length, you can find this in all the models that we have nowadays. Okay, if you can find these two, then you can find the profile for your dimensionless shear, right? Okay, so we have defined this dimensionless wind shear, and using the similar idea, we can define the dimensionless potential temperature. So very similar to this one. Okay, the potential temperature profile, replacing this one, the shear, and then we have the term analogous to this U asterisk, which is called the surface layer temperature. Here, this one, the theta asterisk. And this kind of dimensionless potential temperature profile, you can call this, because it's change over height, right? The profile, the dimensionless potential temperature also depends on the Oberkopf stability parameter. It should depend on the dimensionless height. Okay, so we have like a new definition for this, which is similar to this momentum exchange. This is heat exchange, right? We have the similarity that we can find from the momentum exchange, right? This is heat exchange. So very similar, we have the similar, you don't need to remember this, you don't need to know the details, you just need to know the profile, right? Here. And we have different Ks. Remember that this one is the K, the reference K for the heat exchange for the K theory, right? Okay, so very similar idea to this one. We normalize things and then put them on a graph and then try to find the relationship, try to find a universal relationship, dimensionless variables here. Oh, the X, okay, it turns out that the flux is also dimensionless here, divided by something. Okay, I forgot to explain this. So here, this one, we apply similarity theory. So these are measurement for heat flux over different heights and over different times. So if we make the height dimensionless and then we divide the whole term, the whole heat flux term with the surface heat flux at that time, okay, then you can see that the lines, they align with each other. The empirical relationship can be developed. So this is called dimensional analysis in the book. Okay, if you're interested, you can tap into this. So we, just the half of this course, we have just covered a lot of the things. This is chapter 9, right? Okay, so these are the measurements. You can see that they align really well with the empirical relationship. So the dots, why do we call this similarity theory? Because they are similar to each other, as simple as that. So it's not really a theory, it's a parametrization that we do. to get around the things that we don't know. Okay, we don't know much about turbulence. That's why we need this. We cannot study all the eddies. We cannot study all the molecules in the atmosphere. So we need to use like a method to go around the actual science, the actual physics. Then we do this, we do the parameterization. Okay, so you can apply similarity theory to different things. They have a lot of different graphs like this one in the book. I just have shown you one. Okay, so what we do is that we define some dimensionless variables, and then we try to find the relationship between the variables. It doesn't mean that you will always find them. It's just pure luck, okay, for someone to find this. Of course, you need to do the groundwork of making everything dimensionless, okay? And the result is an empirical equation or a set of curves that look very similar to each other. So it's called similarity theory. And this only applies to the equilibrium state situation, okay? And of course, people have gone through a lot to find this different types of similarity theory. And this is called zeroth order closure. So last time you have the first order closure, right? You have the first order closure, you still have some change over time, but now you have no change over time. So it's called zeroth order closure. Which is also applied to the mean variables. The mean variables doesn't change over time. Okay. We have time to finish everything. Okay. So this time we talk about parameterizations in the interface. So the interface has been really challenging when we talk about Earth system science, when we talk about Earth science. Any type of interface is very difficult. For example, the interface between air and the solid land surface, or the interface between the air and the water surface. The exchange is really hard, okay? So we only have approximations for that. We have the K-theory, right? The K-theory is describing the flux relating to the gradient. So here we also apply this, we parameterize this vertical flux of something. This something is this eta here, okay? So this eta, this variable has two values. At the top of the surface and at the bottom of the surface, we have two values. So the gradient of them will drive the flux, and then it has to be down gradient, so negative. So this thing is controlling how much the flux, how much your properties is being transported through this surface, through this interface. So we have what we call the transport velocity across the interface, and the flux here is driven, this one, sorry, is driven by the gradient in here. So the wind speed vanishes to zero. So of course there's nothing in the surface. It's a solid, right? It's a solid surface. So this eta bottom is zero, and then ut, okay, this one is zero, most of the times, okay, and this one is not zero. And ut here is not the actual wind, is referred to as conductivity. I don't know if you have already heard of this. So the conductivity or the conductance, so this is analogous to what you learn in E&M. So conductance here multiplied by voltage potential. These two can be compared to the voltage potential. The voltage potential means the difference between the voltage, okay? And then it would equal to the current, equal to how fast your properties is moving. Okay, so the job here is to parameterize UT. Of course, we can measure these, right? We want to find the flux. We want to parameterize this. So for different situations, you should have different UT here. For example, if you have different surface, different surfaces, different types of surfaces, you might have different UT, right? If it's rougher or if it's smoother, then you should have different UT. So here we parameterize this in terms of the wind speed. Okay, so this is like a first assumption for any type of flux transport, right? So M bar here, it only means horizontal mean wind. Okay, it's representing the strength of the wind shear and hence the turbulence. So you include the strength of the turbulence in here. And then CD is just a bulk transfer coefficient, which is representing the properties of your surface. Okay, so on top of your PBL, remember that you will have great wind shear on top of the PBL, right? You have the wind, and then the height equals to the boundary layer top. Okay, and the entrainment velocity, I don't know if you remember this, entrainment is the inclusion of the free atmosphere air into the mixed layer. Okay, so it's studying the flux, the air coming from the free atmosphere into the planetary boundary layer. We're not covering this in this course. If you want to read more, you can read this part of the book. Okay, we are only covering things happening near the surface in this course. Okay, so the flux of wind, now we replace the eta with M here is for the flux of wind, right? Or the wind flux or the momentum flux. Okay, so here the flux is driven by the difference between the mean wind, and we parameterize this UT as the M bar again, in terms of the M bar again. So we can replace the whole thing, replace the UT by this parameterization, right? So now you have CD and M bar square. Into different dimensions, this is what you have UT, you have replaced UT in here. You have zero wind speed at the surface, right? It's always zero at the surface. So you only rely on this speed on top. So U bar here is the speed on the top. V bar also speed on top. And here, if we apply this whole idea for the momentum flux, this is called the drag coefficient. So you always heard about the drag, right? The drag is talking about the friction. So here we call this drag coefficient because it controls how much your momentum is being transferred to the air. And here the C is called the bulk transfer coefficient of heat. So very original. So we already called it bulk transfer coefficient. So it's just a term relating the flux and the gradient. Also this one. Okay, so one problem is how to specify the surface value. Okay, this one is tricky because you know that there must be some heat transfer from the surface to the air, right? It's not zero anymore. If you talk about momentum, then it's zero, right? Zero speed at the surface, but this one is not zero. Okay, so what is air drag or air resistance or air friction? So all fluids have intrinsic friction due to two effects. The first one is the weak attraction between the fluid molecules, which is the viscosity. So the larger the viscosity, the larger the attraction between different molecules in your fluid. Okay, and then also the transfer of momentum from the fluid molecules that bounces off the object. So this type of transfer of momentum. So friction are coming from these two. And there are different types of drag in here. The first one is the friction skin drag, which is coming from the small size obstacles like blades of grass or trees. So it's a drag from the molecular diffusion, which means that it should be very close to your objects, just molecular diffusion. So it's called skin drag because it's very close to the skin, right? And then the form drag, which is arising from large obstacles. So if you have a golf ball, you have this type of drag, right? So it's the dynamical pressure differential formed by deceleration of air. So here, the wake behind this ball. Or the wave drag. So if waves are formed behind your object, then you have another types of friction coming from the waves due to buoyancy. So the gravity waves that you see from the satellite, that would be wave drag. It has to have gravity comparing to these two, right? So now we have covered two methods. The first one is the Eddy covariance method. So you might be more comfortable with this because you have come all the way from the TKE equation, right? From the momentum equations, then you develop this K theory and mixed length theory. And now we have the profile method. So both methods are legitimate actually, because CD you can just assume a certain value for different cases, for different surface, right? So this is actually very similar to K theory. Okay, so these are the reference values for your drag coefficient for different continents. So if you do simulation, if you do like a very large scale simulation with cross resolution, then this is, you might want to apply this in your model. They are constants because they are for statically neutral conditions. Okay. So here we talk about constants, right? CD is like a lookup graph, a lookup table in here. So you look up the numbers and then you apply that to your situation. But sometimes you have to have another type of parameterization for your CD. Sometimes it could depend on height again. Okay, so here the surface temperature is defined as the temperature at 2 meters, and then the surface wind is defined as the wind as 10 meters. So that's why if you see some tower doing PBL measurements, sometimes you have like two levels of instruments. One is at the 2 meter level and one is at the 10 meter level. Okay. In numerical models, the height would be the lowest grid point. So they should be the lowest grid point. Okay. If we recall everything we have learned, the K theory, the friction velocity, and the mixed length theory, this one, which is expressing your K with height, okay, and also the log mean profile. You know that your CD or your drag coefficient should be decreasing with height. This one, right? If you're looking at the surface level, so you compare these two, maybe comparing with this one, comparing with this one. Right? Your K depends on height, so your CD depends on height. Okay, we are doing comparison between the two methods in here. The first one is the Eddy covariance method, and second one is profile method. So you know that CD might not be constant sometimes in different situations. Of course, this is talking about the surface layer. So in surface layer, you might have different expression for your CD. So if you do the math, okay, combine things, and then you combine the two approaches here, you can express the CD as the, again here, this is normalized height, and then the von Karman constant with, you have no unit in here, okay? So it could be depending on height or the roughness length. C0 is the roughness length. So this is how you include the roughness into this drag coefficient. Okay, so there are different reference values for different situations. You can see that over plains or nighttime, over snow surface or winds over water, they could be different and they could be depending on the wind speed. The M here is the wind speed. Okay, and we have talked about the drag coefficient depending on height, but actually drag coefficient could be depending on the stability situation. So this one is for the statically neutral conditions only. Okay, so if you have unstable situation, what would happen? The transport, you assume that the transport would be larger, right? The transport rate for the unstable flow would be larger than the neutral flows, right? So we have to do something to this drag coefficient. We have to include the stability parameter. We have talked about this, right? This is the stability parameter. So this is the, what is this? This is the output curve. Let me see that again. Okay. This is, okay, never mind. This is what we call stability correction terms. We want to include it to include the stability conditions. Okay, and we don't just want to include the stability condition coming from the momentum term. Of course, we need the heat flux term, so we rewrite this equation with these two terms in here. So the two terms in here can be expressed in terms of the two phi's in here. The two phi's, what are they? They are the dimensionless wind shear and the dimensionless potential temperature profile. Okay, and you know that they are a function, the dimensionless wind shear and dimensionless potential temperature profile are the function of the dimensionless height. Okay, let me go back. It's very confusing. This one, right? Okay, so the dimensionless shear is a function of the dimensionless height, and the dimensionless potential profile here is also a function of dimensionless height. So this is what we are talking about, that slide. Okay, so what we are trying to do is that we're trying to include the stability condition. So for the stable condition, your phi here is smaller than 0, which means that you might have smaller, you have a larger term here. So you have a smaller CD, reducing the turbulent mixing. So stable condition will reduce your value of the drag coefficient. So this is how we include all the things. We include the height dependence, we include the stability dependence to this drag coefficient. Okay, we call this stability correction terms. So how do we move forward from here? We actually do integration. So we integrate your dimensionless wind shear over height. So you put this, you don't have to do integration for this, but this is how we arrive at the result. So we put this partial z over left-hand side, and then we do integration. Of course, we perform the integration over this also, because it's changing with height, right? This one changing with height. So we do integration for this, and then do integration on the right-hand side, which is pretty easy. And then what you find is your wind profile over height, and also is changing according to the stability condition. Okay, so these are the details after you have do the integration. Don't worry about them. So the log wind profile, comparing to the log wind profile that we have already learned, very similar to this one, right? Very similar to this one, except for the stability correction term, which is coming from the zero border closure, which means it's coming from parametrization. Okay, So we include the parameterization into your log mean profile. That's the meaning for this. So that's why last time you have this neutral log mean profile. It's the y-axis is in log scale, so it's not log mean profile. It's a straight line, but this is log scale. Okay, so originally, if you have neutral condition, this is your profile, right? This is the logarithm mean profile. But if you include the stability correction term, your log mean profile will be changing due to different situation, unstable or stable situation. Okay, so that's the whole idea behind what I've just talked about. So this part, I don't think I will include this in the exam. It's too. Okay, but you still have to do the classwork. 9.1 and 9.2. Okay, so next time we come back and talk about this. Any questions? Any part you want me to repeat? We have some time left. All parts. Okay, no parts because it's not in the exam, right? I will tell you which part will be in the exam, which part are not. Okay. Okay, if you have no questions, then that's it for this lesson. Thank you. Yeah. 佢冇咩？佢咪有佢？係。唉，呢啲嘢就算啦。係喎。算吧。會太深究呢啲，都係做嗰啲 research 先會深究，我覺得。係啊，禮拜五啊。禮拜五係要俾個。係啊 ，send 俾我。禮拜三要翻埋。禮拜四啦，禮拜四教。我而家做，你即係搞掂啦。諗嗰啲咯，但係你搞掂。哦，好。禮拜四之前。好。